Today, students, we will see a very important point about the electrode potential. So, in the previous video, you have seen about the electrode potential, that potential developed between metal electrode and its own ions, or it can be between metal electrode and a solution. So, we'll start with this. So, we'll see now the different conditions how the electrode potential is affected. So before starting, I am going to tell very quickly about the type of electrode potential. So electrode potential is of two types. First is oxidation potential. So when the potential is obtained, potential is due to the oxidation. And what is oxidation? Loss of electrons is oxidation. Let this case be the metal ion is there. And so how it is formed? It is formed by the loss of electrons. See how? We take the metal and the metal undergoes oxidation and electrons. So here the potential measured will be oxidation potential. Now second is reduction potential. So reduction potential, reduction is the gain of electrons. Let it be anything, any other metal. Suppose it gains the n number of electrons and it forms the metal. So this measurement is oxidation potential, this is reduction potential. So it is of two types. And how potential is developed? Actually, potential cannot be developed on a single metal piece or single metal electrode unless until it is not dipped into metal solution. Because metals are electropositive in nature and metals have tendency to lose the electrons. Again I am drawing it. Let this be the beaker or any vessel, and here we have this metal, and this around it is the metal salt solution. Now as the metals are electropositive in nature, so metals have tendency to lose the electrons and acquire positive charge, and this is the electropositive nature. Now this metal electrode, this is the metal electrode, and it will undergo oxidation like this, and around this reaction takes place at the surface. It cannot take place inside, it will take place outside the surface, and here electrons will be accumulated. And electrons will be here inside, and outside the electrons there will be the metal ions. So metal ions will be there. So the point is that the metal ions will be just outside the surface and electrons will be just attached to it. So here there will be the potential developed. Here there will be the development of potential. So here there will be potential developed, but this potential is very, very small. And for the larger potential, we have to take into consideration some appreciable development of the potential. So this electrode potential is defined as a potential developed between an electrode when it is dipped into a metal salt solution. So this is electrode potential. Now electrode potential is of a very important point. We are able to know about the reactivity, how it is affecting different conditions. I will say the factors affecting electrode potential. What are the factors affecting? So first is the temperature of solution. Temperature of solution is one of the factor. You might be knowing that in the winter season, it is very difficult to start a vehicle by the battery or by even by the kick, because by the self start, the temperature is low and so less ions are available due to less mobility, and so it is there. So this is one point, that is the temperature. Now second is the concentration. Concentration is also an important factor. We have to top up the batteries which are used in the automobiles, vehicles. They have to be top up with the suitable amount of water, suitable concentration of acidic water. Very little amount of acid is added in battery water to maintain the standard strength of the metal solution, and so it is the second point, concentration. And third point, of course, is the nature of metal electrode. This is the third condition. Metal electrodes, all the metals are not equally electropositive, or all the metals are not equally reactive. Different metals have different activity, and as a result, the difference of the electrode potential, it differs from metal to metal. All the metals do not have equal amount of electrode potential. This is due to the nature. Nature is decisive factor. For example, iron is very reactive, zinc, aluminium is very reactive, but silver, gold are least reactive. Silver, gold are called noble metals. So this is the reason. Now coming to children, a very important point, a standard electrode potential. We will see about the standard electrode potential, and this electrode potential, it is represented as E naught. So standard electrode potential is defined as the electrode potential developed when a metal electrode is dipped into solution of metal salt and it is measured under standard conditions. And so what are standard conditions? So children, standard conditions are certain norms, and out of one is use of standard electrode, and the temperature, room temperature 25 degrees Celsius or 298 Kelvin, and the molar concentration of the salt should be 1 molar. And fourth point is the hydrogen gas pressure. Pressure of hydrogen gas is taken as 1 atmosphere. Now these 4 points here, there is nothing like that. But what to do? This is measured by a standard electrode, and let's see what is standard electrode and how it works. This is very important part, measurement of a standard electrode potential, and it is represented as E naught. So before starting, first see the construction of a standard electrode. So a standard electrode, first we see a standard electrode. Actually, children, just I had said that a standard electrode is a special type of electrode, and certain standard conditions are maintained or created, or the conditions have to be taken into consideration. It is very simple arrangement. Actually, there is a beaker, and the beaker contains 1 m acid solution. There is 1 m acid solution, and here temperature of this experiment or setup, it is maintained to be 298 Kelvin. So this is one condition, this is other condition. Now see, here there is the beaker, and in the beaker there is a glass vessel. There is glass vessel, and the glass vessel, it is a special type of tube, and there is a side tube, and there is an inlet for the gas. Now see, inside the glass tube. This is, let be the glass jacket. There is platinum wire, and this is platinum plate coated with black platinum powder. Black platinum powder, it signifies very fine, powder, ultimate form of powder. Black platinum powder, it is very, fine powder, and the nickname is there. So see the conditions. Here there is pure and dry hydrogen gas at 1 atmosphere. So this is the third condition. So this is the first condition, this is the second condition, this is the third condition. So this is called as normal hydrogen electrode, NHE, or it is called as a standard hydrogen electrode, or it is called as SHE, NHE or SHE, and both are same because the three conditions have to be maintained. The pressure of the hydrogen gas passing through the tube should be 1 atmosphere. Here the concentration of acid should be 1 molar and temperature should be 298, and let this be the acid solution. So why we pass, the question is why we pass the hydrogen gas? Children, actually it is normal hydrogen electrode, so normal conditions of the hydrogen, or it is standard electrode, and more precisely or scientifically we call it as standard. It call it standard or reference electrode. Reference electrode means the electrode potential of any unknown electrode or any other electrode is determined, or it is calculated using this only. So it is a reference scale, it is a reference point. Suppose we consult something, so we go for consultation with book which is standard book, so that is called reference book. Is that clear? So this is there. So this is a standard hydrogen electrode or normal hydrogen electrode, or it is more accurately called as reference electrodes. So reference electrodes are of different types. So this is normal hydrogen electrode. Other is calomel electrode, which is not in your course. Calomel electrode. So calomel electrode, actually it uses mercury chloride. Mercury chloride is used, and there is mercury, and it is in a boiling tube. So it is there. Now certain conditions that by default the standard electrode potential of this, and here children see very important point. Here we can write this, and it is equal to 0 volt, and here we have, it is said to be 0 volt. Now this is what? There is a reaction. Hydrogen gas means H2 is converted into 2H ions. In this condition, 2H ions are gaining 2 electrons, and there is formation of hydrogen gas, and so this is there. Now what is very important, that this is called as oxidation half cell or standard oxidation potential. This here it is 0 volt. This is the reduction gain of electrons. So it is 0 volt. So what is important? Important is that in a standard electrode, hydrogen gas is passed to maintain the standard of 1 molar, because as this hydrogen ion present will undergo oxidation, it will undergo reduction. So this hydrogen gas is passed so as to maintain the standard strength of the solution. And so this is the point is that this SHE or reference electrode can act as oxidation half cell, or it can act as reduction half cell. So here it will act as what? It will act as oxidation half cell, and here it will act as reduction half cell. So NHE or SHE can go in either way, and thus it is called as reference electrode. Coming to next part, which is very important part, how to use this reference electrode or standard electrode. So children, as you know, it has electrode potential value of 0 because it is reference. It has not any value. So you have seen in your previous class that E cell is equal to E right minus E left. E cell is equal to E right minus E left. Or you can say, in standard condition, E standard cell is equal to E standard right minus E standard left. Right means right electrode, left means left electrode. So this is the point. Now this convention, here we write or draw anodic part, and here there is a cathodic part A, B and C. So see how. Now see, I am going to draw other electrode with this, and we will see about the determination of standard electrode potential of zinc electrode. How to determine the standard electrode potential of zinc electrode. So here again same condition. Here we will take the zinc sulfate solution, and there will be the zinc electrode, and now it is connected to this SHE or reference electrode, and here we have the voltmeter. So as it is anodic, so it is the anode, and so this will act as cathode. So here there will be the oxidation, here there will be the reduction. So it will act as negative, it will act as positive. So electrons will flow like this, and current will flow. Current flows from positive to negative. The direction of flow of current is from positive to negative. Now on completing the circuit, let's draw the solution, and we'll complete the internal circuit. And this is what? This is salt bridge. This is salt bridge, and so this is there. And children, at the salt bridge there are the cotton plugs. These are the cotton plugs. These are cotton plugs. This contains strong solution of strong electrolyte like KCl or KNO3 in agar-agar and still water, and the end there is the cotton plug, because it is in solution in water, and so it will undergo slowly degradation or decomposition. Now reaction will take place. Reaction will take place. And this voltmeter will indicate the deflection. There will be the deflection. It will indicate the deflection, and it will have this cell. This is a cell, and there will be 0.76 volt. The reading in the voltmeter will be 0.76 volt. Now we know this formula, so we'll put here. So E standard cell, E right. So right is what? This cathode, reference electrode. So E right, it is 0, it is 0, it is 0, it is 0 volt. And here this anodic portion, this is left hand point, and let it this with the this left. But here it is as it is 0.76 volt, and here it is 0, and so it is there. So left electrode, so E left. So what will there? Or we say E standard left is equal to minus 0.76 volt. It is minus 0.76 volt. So this is there. Now coming to the writing of net reaction. How we write the net reaction for this electrode? So it is written just in the status class. So first we take the zinc solid, then one line indicates the vertical line indicates the separation. So here we have the zinc aqueous, let it be 1 m. It is symbolic, whatever you take the concentration. Then the two lines, this indicates what? This indicates salt bridge. Again here we have the 2H ions aqueous, and it is standard, so it is again 1 molar acid solution. Here we have this this H2 gas, and here we write 1 atmosphere, and here we write the platinum solid. Some persons do not write this platinum, but this should be written because this is used as a medium to pass the way. So this is the net reaction. This is the net reaction for measurement of electrode potential in zinc electrode. So this is there. This is the measurement of this in zinc electrode. Now see, I will see again about this other half, that is the copper electrode. See how. Now this I have drawn two beakers, two half cells. Now we'll see. Again here we will see the standard electrode in that condition. So here there will be the this SHE, because the condition of SHE will remain same. The position of SHE will remain same. So here we'll have the same arrangement, and there will be the same condition. H2 pure and dry at 1 atmosphere, and here there will be the again platinum, and this is the 1 m, and again here there will be the 298 Kelvin temperature. Just quick revision. And here this is this is 1 m copper sulfate solution. Here there is a copper electrode. There is the salt bridge. This is salt bridge. Here there is the, this is the voltmeter, and same. So this is a standard position, and it will again, now here there will be the flow of current, and here the deflection will be 0.34 volt. And so we know the formula that a standard cell is equal to a standard left minus a standard right. So this is there. So here it is E cell. This is cell potential. This is the voltage, or this E cell, standard cell. So here it is 0.34 volt, and so this left, and so it is unknown, and so here it is 0. So here, or the value of this E of left will be equal to plus 0.34 volt, and so this is there. Now writing the net reaction. So net reaction can be written as it is. So here we write here this copper solid, one line, copper ions aqueous. Here it is 1 m, then 2 lines. Again same conditions, 2H H2, here 1 atmosphere, and again there is the platinum. So this is the net reaction. So children, in this manner we determine the electrode potential of any unknown electrode or any electrode, but this position will remain same, or it will remain as it is. So this is the way we find out.